I'm Keegan Maddern.
And I'm Alex Wurr.
And today we're going to be talking about hydraulic jumps. Now, you see these every day, normally in your kitchen sink. When you have the water in your faucet on high enough, you'll see a ring created on the bottom of the sink bowl.
Any plate or bowls or any other like dishes or things that you have in the sink that water's flowing over.
And what it appears as is that there's an area right around where the water falls that is a low height, and then there around the ring that the water actually raises in height and can be several times thicker than the water flow right near the faucet. And the physics behind this is actually has to do with a similar form to the subsonic and supersonic type of waveform seen in air, but in this case in fluids, of course.
Liquids.
And liquids, yes, liquids. In this case, rather than called supersonic and subsonic, it's called supercritical and subcritical. In subcritical liquid flow, the velocity of the waveform inside the fluid is actually faster than the velocity of the fluid itself. However, in supercritical fluids, the velocity of the wave can be slower than the velocity of the fluid itself. And this is measured by the Froude number, which is shown here to be the square root of the fluid squared over gravity times the depth of the fluid. So the Froude number, when it's equal to 1, is at the critical point. A Froude number of less than 1 indicates subcritical flow, and a Froude number greater than 1 indicates supercritical flow. And so this diagram shows how at 1 you see no hydraulic jump because the fluid flow entering the area where you would see a hydraulic jump is exactly the same as the fluid exiting. Here, with the Froude number greater than 1, you see that a high velocity flow enters and at the critical point becomes a low velocity flow of much greater height, and you have here a small turbulent area where this jump takes place. Now, this doesn't actually happen in nature because what you have here is subcritical flow going to supercritical flow, and would require some sort of instantaneous acceleration on account of the liquid at this point, which doesn't happen. But it's worth mentioning just because of the physics of the equation. So this equation determines the actual ratio of height, the exit height, enter height, the enter velocity, gravity, which is a constant, and the enter depth of water. And so this equation will basically define all hydraulic jumps you can come across. And if you notice that the critical component of this radical here is actually the Froude number in a different form. And so as the Froude number of your entering flow increases, the height ratio of the fluid of the hydraulic jump actually can increase dramatically. For Froude numbers of approximately 1.5 to 2, the hydraulic jump you'll see is maybe 1.5 times to 3 times as high. Well, when your Froude number becomes on the order of magnitude of 9 or so, the hydraulic jump ratio can become on the order of 12. And this has no real scaling properties, and so you will see this type of scale even on very small flows or very large flows. And now we're going to do a practical demonstration.
And now we're going to give a demonstration of where you will see the different hydraulic jumps of a Froude number equal to 1 where there's no hydraulic jump, or a Froude number greater than 1 where you'll see a vertical jump up as the fluid flows along in an everyday application in your kitchen sink. So right now it's demonstrating a Froude number equal to 1 where the input velocity is slow enough that it does not induce a jump of any kind in the fluid as it flows from its inlet state to its outlet state. But you can see as you increase the velocity, it begins to create a lower depression in the center that then causes a jump up on the edges of the inlet state. And as you increase the velocity, you can see that the jump gets taller and taller, and the ratio of the heights increases as a function of the inlet velocity squared. And you can also see as the velocity increases even further that with the bubbles you can see how much turbulent flow is passing through due to the higher speed waves passing along the upper portion of the surface. As you increase even further, you can see there's a very distinct amount of turbulent flow on the outside that's dissipating a very large amount of energy to the outside flow and is really inefficient.
As you can see from the demonstrations, lower velocity input flows with a lower Froude number have a much smaller jump and therefore a corresponding smaller dissipation of energy, usually on the order of anywhere from 2 to 10%. When you get to a middle range Froude number of 5 or so, you can see dissipations of energy of approximately 30 to 60%. And for the extremely large Froude numbers of 9 or so, you'll see dissipation energies anywhere from about 75 to even upwards of 90-95% energy dissipation. And the interesting thing about this is it's often used in engineering applications to exactly dissipate energy, noticeably in hydroelectric designs. When water flowing through the dam exits, it's usually at a very high speed, and therefore a tremendous amount of force can be exerted on the surrounding ecosystem, rock structure, and even the buildings themselves. And to do this, the engineers will actually design specifically created structures to generate large hydraulic jumps, especially with those engineered high Froude numbers that will dissipate massive amounts of energy through turbulence without destroying the surrounding structure, because all of the energy dissipation happens inside of the actual material itself instead of dissipating itself in kinetic energy upon the structures. And in this way, the structures themselves remain roughly vibration free, while inside the wave, contained with that in and outer shell of low velocity flow, is the turbulent high velocity flow inside. And in this way, it can dissipate large amounts of energy.
As you can see, the Froude number is equal to the velocity divided by the square root of gravity times the initial height of the input fluid. And so the way to an easy way to increase the Froude number is to either increase your input velocity, or you can just decrease the height of your initial input fluid. So as you can see from the table that we've devised by going through different calculations of the ratio equation for heights and the Froude number, is that with a Froude number of 1, there's no hydraulic jump and you don't lose any energy due to the turbulent flow that a hydraulic jump will cause. And as your Froude number starts to gradually increase from a value of 1 to upwards of like 5 to 9, you can see that it goes from being a standing wave that it has a steady jump that just goes up, to being a small series of waves as it gradually keeps increasing, to an unstable jump, and then it becomes a more stable jump as the velocity increases, because then the two fluids are getting a little bit closer to each other and they're able to be more steady. And once you reach a Froude number of above 9, it becomes a defined but very, very turbulent jump, which, due to that extreme turbulence, causes an energy dissipation of 70 to 80% of the internal energy of your fluid flow. And you can also see that with that extreme energy dissipation, you also get a very, very large change in heights. So if what you need is a change in height and not to keep the energy and velocity of the flow, then you want to make sure that you have a very high Froude number. Whereas if you want to retain the energy but not have a very high jump, then you want to keep the Froude number relatively low.